Homework 5.1, System of Equations, Video 4. Homework due Friday, May 29th at 11:59 p.m. This video and the following video are associated with homework questions 5 through 8. In the previous two videos, we discovered a technique for solving a 2x2 system of linear equations using substitution. In a nutshell, you solved either equation for either variable, that created a substitution. Then you use that substitution to rename something in the other equation. That gave you one equation with one variable. You solved it, got half your answer, put it back into the substitution to get the other answer. Except as we saw in the last video, it's not always that smooth, because fractions often sneak into the mix, and although in theory we can all handle them, I understand that they are inconvenient, and it would be nice if we could avoid them if possible. So I'm going to show you another technique called addition. Now, in some books this is called combination, in others it's called elimination. In this book and in the homework it's called addition, which is exactly what its name implies. We're going to add some things. And you may recognize that this is the exact same system of equations from the previous video. So we already know its solution. X was 5 and y is 4, but I don't care about the answer. I care about what's the most efficient way to get there. And if you'll notice, I've kind of already set up a how to solve a 2x2 system by addition flow. It is 4 steps, and if you'll notice, the third step is the same as before. So what's addition? What's the motivation for it? Well, the motivation is the same as it was before. You can't solve for one equation, you can't solve for one variable when you have another one in the way. So either equation can't be solved for x or y and get a value because there's too many variables. So the motivation is to make a variable disappear. With the substitution technique, we made it disappear by renaming it with something that was equal to once we created the substitution. But in the addition technique, we're going to make a variable disappear using a different approach. Addition, as the name implies. Here's the thing we're going to take advantage of. Everybody knows that you can combine x's. You can add x's together. If I added these, I would get 8x. Everybody knows you can combine y terms. If I added these, I would get negative 6y. And everybody knows that you can combine constants. If I combine 33 and negative 17, I would get 16. But what some people don't know or have forgotten is that you can actually combine entire equations if everything is lined up. The x's, the y's, the constants, and the equal signs. So if everything is lined up, you can add the equations together to create a new one. Now, whenever I add equations together, I'll draw a line and draw a really fat plus sign to indicate that I am adding larger objects besides just individual terms. I am adding entire equations. It's my own personal notation. It's okay if you just put a regular plus sign here. If I were to add these equations right now, I would get 8x's, I would get negative 6y's, the equal would stay the same, and I would get 16. But this doesn't fix things. I just have a different equation that still has too many letters in it. But what if, when we added, something canceled? Now, they didn't, like the y's didn't cancel. Like if this were an 8y, then these would have canceled. There would have only been an x and we could have solved it. Unfortunately, it wasn't an 8y. Yet. If we could set up opposites here, or here for that matter, but if we can set up a pair of opposites on the x's or the y's, then adding the equations will make that letter disappear, leaving us with one letter that we can solve for, and then we can go back and pick up the second letter later. But currently we don't have opposites, but can we make them occur? The answer is always yes, we can. Because we have tools at our disposal. Anytime you have an equation, whatever you do on one side, you do on the other. If you add 4 on one side, you add 4 on the other. If you subtract 4 on one side, you subtract 4 on the other. If you multiply by 4 on one side, you multiply by 4 on the other. Wait a minute. I can make this an 8 by multiplying it by 4. But if I multiply by 4 on the left, I have to multiply by 4 on the right. We're going to do that. It's going to set off a chain of events, and this equation, this system will be so easy to solve. So let's set up our approach. I'm about to sneeze. Excuse me. Yeah, that was a loud sneeze, but I'm a firm believer that holding in sneezes is not good for you. So, at least I'm the only one in the room, and I use a Kleenex. Sucks when you're in public, though. All right, so here's going to be our strategy. Number one, if necessary, because sometimes, as you'll see in the homework, you will already have opposite terms set up, so you can skip the first step. If necessary, multiply one or both equations by, and I'm going to put in quotes, well-chosen numbers, and I'll tell you how to choose a number well in a moment. If necessary, multiply one or both equations by well-chosen numbers to set up a pair of opposite terms. Now, sometimes you can just look and spot it. Hey, if I multiply the 2 by 4, it'll turn it to an 8, and that'll cancel. All right, well, let's do that. Now, the way I'll usually do this is I will set up my multiplications, but I'll push everything to the right. So let's just do a gigantic arrow here pointing everything to the right. So if I multiply the top equation by 4, I will get 20x plus 8y equals 132. Use a calculator if you feel. I didn't adjust the bottom equation, so it's still 3x minus 8y equals negative 17. And if you'll notice, I've got my opposite pair of terms set up now. Your second move is add the equations. That's all. If you did the first move correctly, you should be left with one letter. When I do a giant addition, again, that's just my own notation, a super plus sign. When I add these equations, I will get 23x's, but the y's will cancel. And on the right side of the equal sign, 132 minus 17, it looks like it's 115. Let me double check that. Yes. This is easy to solve. Divide by 23. Oh, dividing by 23 usually does not come out well. But guess what 115 divided by 23 is? It is exactly 5. Good, because wasn't x equal to 5 previously? We still have to solve for the other variable, but unlike substitution, we don't have a substitution to substitute this into. In other words, we don't have something that says y equals to substitute the x into. So how do we get the value of y? Well, we still substitute the 5. We just substitute it into an original equation. So for the fourth step, substitute the known value. Substitute, not substitution. Substitute the known value into any equation and solve for the unknown value. I'm going to throw an asterisk on this. You'll see why in the next video. Don't get me wrong, it will always work. So let's take the 5 and substitute it into any original equation. Choose whichever one looks best for you. I'm going to choose the top one. Why? No negatives. If it's the correct x, it won't matter. In fact, it's an easy way to see if your x is correct. If you used both equations, they should both give you the same y value. Let's use the top equation. 5x plus 2y equals 33. Substitute 5 for the x, so we get 5 times 5 plus 2y equals 33. 5 times 5 is 25. Plus 2y equals 33. This is an easy equation to solve. Subtract 25 from both sides. We get 2y equals 8, and divide both sides by 2, and we get y equals 4. So just like before, 5 comma 4. Personally, I prefer addition. and only use substitution when it is ready to go. Because how many fractions did we run into here? None. As opposed to the previous attempt using substitution, there were fractions all over the place. We'll do another example of an addition approach to solving a system, one that shows why you would want to multiply both equations and how to choose well-chosen numbers.